Yeah, now you are.
Okay. So thank you. Yeah, thanks for coming and thanks for the introduction, Luca. Yes, I'm going to talk about a person, Licklider, who probably no one knows. In fact, his wife was kind of upset about this, that nobody knew who he was, and said, you are just giving away ideas all the time. Why? And he said, doesn't matter, actually. It doesn't matter who implements the ideas. As long as they get out there, I'm happy. So he was actually one of the humble people of our field that really enjoyed bringing together the people that would then go ahead and implement the ideas. So this talk is going to be a little bit different maybe from some of the Pearls of Computation talks in that I do not present any algorithms. I will in fact talk mostly about vision and ideas today. So just to get started with a little bit of biography. So he's born in 1915, Licklider is. And by the way, he told everyone just to call him Lick, even acquaintances or people who didn't know him at all. He just said, okay, forget that long name, just call me Lick. He did his bachelor's. He was very smart. He kind of didn't really know what he was going to go into. So he picked several fields for his bachelor's degree. That was physics, mathematics, and psychology. So he was doing all of them at Washington University in St. Louis. And then he went on to do a master's in psychology. And that's what his background is, psychology, not computer science. And then, in fact, in his PhD, he went into psychoacoustics. So within psychology, he was very interested in understanding a little bit more about how humans make sense of sound around them. For example, how people localize sound. How do we know that a sound is coming from that direction and not the other direction? So that was what he was really reveling in after his master's and then into his PhD. He continued that track at Harvard as a research fellow and in fact became a professor in that field at Harvard. And he was publishing in this field, psychoacoustics. He was well recognized for the work in that field. But then something kind of interesting happened. There was a new, very exciting company started in Cambridge, in Massachusetts, called BBN, or Bolt, and Newman. These were the founders, basically, of that company, just straightforward. This was a company that was about the architectural acoustics, or basically how sound is manipulated by architecture and design for new buildings. And this was kind of a new field. And what was interesting about this particular company was that they claimed they could calculate these things using computers. That this was a high-tech startup company with a brilliant business idea. Just bring us, your designs or buildings that you're interested in. We will calculate for you exactly what the acoustics are going to be because we have the machines to do it. And they brought in this guy who was like one of the best in the field, and they put him in front of this, So Licklider and his computer, the PDUN1, was one of the main assets of BBN, just figuring out how all of this complex formulas, these are really complex algorithms or formulas, how you calculate the things, how this man with that knowledge and that machine with the calculation power could solve really hard problems. And Licklider he basically became an absolute computer nerd. I mean, he was basically spent all his time with the machine. Well, that's the other thing that his wife didn't like. So he was just fascinated with the possibilities of the machine, allowing him to do these kinds of calculations. But he was a bit frustrated that there were different places within the United States, different machines that had been devised to calculate different parts of what he needed to accomplish. So the PDP-1 was kind of nice in that he could program he could actually create many different programs on that machine, build a set of tools. But if he wanted to use a tool that someone else built, then when he was out of luck, he would have to find a way to kind of rewrite it for this machine in order to have that in his arsenal of tools. Because of this closeness with the PDP-1 and all of this really interesting high-tech work, and also because he was a part of this kind of exciting business that was springing up, he was brought into ARPA and asked to be the head of the behavioral sciences at ARPA, but also the command and control program at ARPA. And I'll come back to that in a minute, what that ARPA really is. Okay, I am reusing one of the slides from the talk that did not get recorded last time. So now I'm getting a picture of it on the internet, I suppose. But this is time frame. This is kind of putting it into a little bit of a historical context, what is going on when Licklider becomes part of ARPA. And as so many stories around technology in the US, it all began with Sputnik basically, and the Soviet Union apparently winning the race to space, or rather the race to missiles that would destroy any part in the world. So in response to Sputnik being out up in space, the US scrambled, and they did everything they could to catch up and be the more powerful when it came to an arms race. And they employed, as we all know, a lot of technology to win that race, get up there. One of the things that they did was to really bring science close to the government. The government would need some kind of a body of scientists solving hard problems. So there's a special scientific advisor to the president and so on. At the time, mostly it was the different branches of the military that were responsible for advancing in different fields, technological fields. So there was work being done in the Air Force, like the SAVE system, which was like the radar network and alert system, where they could also scramble airplanes into the air with a click of a button in response. Those were within the Air Force. But someone figured out, well, that there's a lot of wasted effort when you have different branches of military almost competing, trying to solve different things, or kind of trying to get money from the other branch. And so now the Navy wanted something, now the military wants something. So the different branches were kind of an inefficient way to really advance the forefront in a single place. So what they did, they founded a special science research program within the Pentagon. So this is actually in the government, essentially, that we call the Advanced Research Project into ARPA. And that was meant mainly to build missiles, to get into space, to kind of win this arms race into space. And that was how they got started. But at the same time, they decided that, well, this is a longer story, but at some point they decided to take it out, that part out of ARPA, and start a new program called NASA, and move all the space missile stuff into this other thing called NASA. Okay, that's a longer story. So shortly after that, all the missile stuff goes into here. And that's one of the things you don't really realize at NASA. Well, it's not so peaceful after all, is it? But what was left in ARPA then was pure science, actually. I mean, that was some of the visionaries. They were thinking, okay, we really need to think about some really, not necessarily in the military context even. We just need to solve some really hard problems, and we're going to focus and refocus on science. But interestingly enough, it was also focused on business. So most of the contracts from the ARPA program were done with the various technological businesses around the US. So there were contracts made with them. Okay, here you get money, you develop this particular line of research. And this is interesting because this kind of information technology and all of that was pretty much almost considered a pure kind of a business venture of sorts. But when Licklider was brought into ARPA as a director of their program that then ultimately became the kind of the information technology program there, he brought in this idea that you really needed to get the universities on board, that you needed to, in fact, try to reduce the reliance on only businesses to do this. So he would start funneling money from business ventures and sticking them into programs that would be controlled by academic universities in the field of information technology. And I'll just pop this up here to make this point. So he started redirecting funding from companies to universities, reinforcing what is kind of called the triangle. Well, you all ever heard about the industry military complex. So the triangle is putting academia in there, and that becomes a much stronger footing for your work. And that's what he wanted to reinforce. And that involvement, there's a direct link from that to the establishment of PhD programs in computer science. It did not exist until that point. No one could get a PhD in anything called computer science anywhere. But these programs at MIT, Berkeley, CMU, and Stanford are a direct result from Licklider being there and saying, now let's make sure that we make use of the universities and their research labs for doing this type of technology. He was also interested in the broad benefits of these technologies rather than exclusively the military aspect of them. And last but not least, that time that he was at ARPA, he formulated this vision for the internet that then came later. And you can see from this timeline, he was in the office from what was it, 62 to 64. That's when he's doing all of this work. He's linking all these things together, creating groups of universities and businesses to solve certain problems. He left in 64. Shortly after he left, the first experiments of connecting between computer centers across the US were made. And this is, I think, between Lincoln, Latin, and Santa Monica. I think there was, that was the first. This was not using any of the protocols of the internet, but it was kind of to show it, with proof of concept, you could say, of an internet-like system. And then in 68, so 4 years after he is already put together some groups to think about this and formulate the vision, there's a call for proposals. So DARPA or ARPA sends out, here is what we need. And there's a description of the internet in a way. Here is what we need. Is anyone out there that thinks they can implement this? And there were requirements in there, including requirements about response times. And big businesses, they would look at that proposal and say, it cannot be done. We're not even in the game. But guess what company actually picked up, actually won the bid? BBN, the acoustics modeling company. Yes, that's the company. Well, okay, they started doing other things, but that was a small player in that, it was not IBM, it was not, they managed to get the contract to build the internet or the infrastructure that would be required and solve some of the hard problems. And just a couple of years later, we have the first nodes of the internet connected through that program. So there is this direct link all the way to the starting of the internet, and I'll come back to that in a bit later. But that said, this is not what I'm going to be talking about most of the time for the rest of the talk, because I'm going to focus on two seminal papers that we wrote. One a little bit before this, that I'm sure was kind of the reason why, one of the reasons why it was brought in fact. which is a paper talking about the human-machine symbiosis. And then in 68, around this time, he wrote a paper about the internet, and he already wrote some things about the internet back here, but he kind of put everything together into an influential paper that comes out around this time to really shape the generations after that. So I'm going to talk about these two papers for the rest of the talk. So let's talk about the first paper in 1960s, and think about this then, that you're talking about a person coming out of psychology, and but this really had people thinking, okay, this person really knows what he's talking about when he talks about technology. So let's bring him in. So man-computer symbiosis. Symbiosis is really when two organisms, they absolutely depend on each other to live. So, and in nature, and this is actually the example that Licklider gave in his paper, we find examples of this. We find examples of if we take one organism away, the other will die, no matter which one you take away. And this example here is the particular kind of a wasp that lives in a fig tree, and basically you could say the reproduction is kind of interlinked. So when these reproduce, they actually do so by taking the seeds of this plant and putting it into the other gender plant, and then that plant gets to create other plants and so on. So it kind of feeds on the tree during its own reproduction, but then also ensures the reproduction of the other species. That's the concept of a symbiosis. A man-computer symbiosis. Well, this is so. In these slides, I am quoting pretty much always Licklider. So assume that those quotes are always from his paper that I'm talking about. So he puts it out there that his hope is that in not too many years, human brains and computing machines will be coupled together. It's a dark vision. That's why I put H.R. Geiger here in the background, if you're familiar with that artwork. But I don't think it's necessarily coming from a dark place. But before we understand really what this is, this human-computer symbiosis, let's think about what it is not. Because you might have some ideas, maybe what this could be. So this is in his words. This is different from the mechanically extended man, which was a field that had already taken, gotten considerable attention. Is to extend man's with machines. That means things like being able to see further through a machine, for example, being able to lift things that are heavier and things like that. So machines were already at that point being used to help man. And here I also want to point out, people say man here to mean humanity and not males necessarily. At least that makes it easier to read these texts usually. So being able to extend human ability through these devices, that is simply just extending the man, but it's not a symbiotic relationship between the two. And then we have also, this is different from mechanical replacement of man through automation or, say, robots or AI that somehow should be able to do it all by themselves, but because we fall short of making AI that can do these things all by itself, it needs a human in there too to help it along. But then you have kind of the reverse thing going on. The human is kind of being used there as an extension. And it is not, again, a symbiotic relationship. It's not both ways. So it's not these two things. And he puts this up in sort of a timeline. He's considering this, that today, well, in the 60s, they are extending humans with technology. In the future, namely 1980, we will have AIs that can do these things all by themselves, but there will be this really exciting period in between where that relationship between the man and machine is going to be very tight to and you'll be able to do things together that you would not have been able to do before. Those years are going to be some of the most creative and exciting in the history of mankind, he thought. So he was quite optimistic about his job prospects, I suppose, in the coming years. But this is important to understand, that he still believed that maybe in some point in the future you would have full AIs that were able to do things, creative things and planning things and so on. Okay. And the aims of man-computer symbiosis, well, if the user can think his problem through in advance, symbiotic association with computer machine is not necessary. So if the user can really formulate everything that needs to be solved, then you could just as well hand the calculation over to the machine and not worry about that relationship. But bringing the computing machine effectively into the formulative parts, into the formulation. For example, asking things like, what is the question, not what is the answer? Or participating in a trial and error dialogue. Those require that symbiosis. Also, when you need to shorten the process, when you need to do something where things require real-time decision-making, and not something that up until this point had been purely a batch process. You had to formulate everything ahead of time, put them on these cards, bring them to the machine. Well, in fact, the way they describe it is, okay, you formulate this thing over a period of a couple of days. You sit down with a programmer for a couple of days that then programs those things onto those cards. You bring those cards to the computer that runs something. And here, in his words, you get 20 feet of paper, of numbers. That is the results of running this. And now you analyze these numbers. And you may even, in fact, have to, well, you might be taking some decision based on this, but only after you have then stuck them into a different simulator that will then provide you with some possible results of using the tactic that was suggested by the system. Anyway, this process here could be several days, and that is too long. So if you need to do something in a far shorter time, you're talking about something real time, then why not just merge the person and the computer to do that fast? Yes, go ahead.
Would you consider something like interactive or improving man-machine symbiosis?
I suppose so, yes. Yeah, exactly, because I mean the formulation.
Like a dialogue.
So it's a dialogue.
Just ask the machine, go ahead and prove this stuff for me. So you formulate some questions to the machine gets back and says there's something missing.
Yes, and then it asks for things, and then you fill in, and that's exactly along the lines, yes. But he was interested, but what is technical thinking? I mean, so he's thinking, okay, well, he is visioning that you are in this process of doing something, but that something, he was still thinking, like, what is that something? What am I doing? And he admitted that he was using himself as a subject to study actually what happens when I try to solve a problem. And then he went through that and he really kind of introspected for a while. And he found out that his thinking time was mostly devoted to activities that were of clerical or mechanical manner. So he was searching, calculating, plotting, transforming, determining logical and dynamic consequences of a set of assumptions or hypotheses, preparing the way for a decision or an insight. So he's spending, I think he said 85% of his time not really making decisions, but actually just sort of setting everything up so that he could really maybe do that little important part at the end. And he admitted his choices of what to attempt and what not to attempt were determined to an embarrassingly great extent by considerations of that clerical feasibility. So he would imagine just sitting there, well, oh, if I could only find that paper, but I can't find it right now, so I'll just not worry about that part of what I'm thinking, or I can't really bring up the program to run this. I don't have it, so I'm not going to do that kind of thinking, things like that. So it's not the intellectual capability, but the incapability of doing all this preparation that maybe stopped him from doing things. So all of that, he then went on to formulating the prerequisites of such a system. What does that system need to fulfill to become a partner in this relationship? And there are A through E here, and I'll quickly review them. So he was concerned about the speed mismatch between man and computers, meaning that he thought computers are blazingly fast at doing all this stuff, and it would be a waste of resources to have a computer bound to a single person, since that computer is so amazing. So we need to serve many humans with one computer. We need networked thinking centers. So this is 1960, and you can already see that's where this internet idea is really coming in. Memory, well, of course, he wanted compact and cheap memory, so you can have masses of information at your fingertips. And he was considering that maybe to make certain types of memory cheap, you would actually have them read only. So like he was thinking of certain memory would be editable, certain memory would not be editable, but faster, and so on. But interestingly, he also proposed, well, maybe we should not store everything in memory. In fact, books are really good. And therefore, well, as long as we have the citations in memory, we can just go and get the book. So yeah, it's kind of a nice, we still use books, in fact. Organization of memory had to be such that you would quickly be able to retrieve from memory, and there were some developments in this area that he thought was exciting, including the data structure for being able to quickly key something to certain strings, because he was interested in that, okay, humans use names to look up things, not like, say, memory addresses or something like that. So we need a fast way of taking a name or something like that, and then mapping that onto, say, a function. And maybe there are lots of functions that we need to be able to index this way, and here's a fast way to bring them. So you can see this is just basically a graphite automaton thing, so like you just follow the links. The first letter that you come across is like T, for example, then that brings you to this node, and then the next letter in the string is O, that brings you to that node, so that you will end up in a particular leaf depending on what string you insert into this tree here. Fast way to get to the leaves. And then in the kind of the general language problem, he was thinking about programming languages as being, okay, we have programming languages to talk to computers. Are we going to use the current programming languages, or do we need something new? And he was seeing two things happening. I mean, he was seeing that there are programming languages like Fortran, I think he mentioned, it's somewhat close to a human language, so that's kind of nice. And we also have developments where people are adopting certain formalisms when talking to computers, and that might be pretty good also. But he still felt that these instructions that these programming languages were used for, they were used for instructing the computer to take a certain course. Like, this is what I would like the computer to do. Whereas the communication between people would not necessarily be like, I want you to go take a step to the left, take a step to the right, and do this following thing, but rather you would communicate your goals with other humans. And so you should be able to talk about goals with computers. And he didn't feel that there was a programming language that was speaking at that level to the computer. And then lastly, which is not the least, is the input-output requirement, or what type of equipment allowed you to communicate with the computer. And at that point in the history, there were some really amazing things happening, namely with especially displays. And I was going to maybe quickly show a segment of the video of the SAGE system. Let me see if...
IBM applied the latest extension of data processing, the display scope, a giant picture tube on which computer results are instantaneously and continuously translated into graphic images. In SAGE, airmen have the battle visualized for them on the computer-generated display. 2 floors above the great computers are the batteries of display scopes. Although they look like the offspring of a marriage between a television tube and a radar screen, display scopes do not show physical images transmitted from elsewhere. They display the results of the computer's findings. SAGE, with its display scope, also has one feature possessed by neither a television or radar screen. It has memory. In case of enemy air attack, not only can a clear picture of the changing air situation be displayed on the scope, but if the airman wishes to see how things got that way, the scope can recall any previous phase of the situation from the computer's memory.
Okay. This is happening exactly when that paper is written. And he was, in fact, involved in some of the SAGE projects through Lincoln Laboratories, which so he knew, he was intimately familiar with the display technology at that point in time and that kind of dialogue that was starting to appear around those displays. But he wanted to go beyond that, and he wanted to go into something that was as convenient as a pencil and a doodle pad or a chalk and a blackboard for interaction. So he said that we needed some kind of a surface display and control that would be just like a blackboard. Would understand basically when you wrote on it. And we would need a computer posted wall display. He was also talking about groups of people interacting with the computer at the same time. So you would need to kind of gather around a larger type of display to share ideas and have the computer participate in it. And lastly, he was also envisioning that you would need speech in and speech out. So the SAGE system that you saw there did not have any speech input or output, but he saw that as a very crucial step in making this dialogue happen. And I thought it was quite funny that one of his motivations for speech recognition was that bosses would never have the time to learn to type. They had people for that. So any computer that would require typing would never be used in decision making at the top. Therefore, you needed speech. And at the time, there was already speech recognition that was capable of recognizing the digits to a 95% accuracy. That's a small vocabulary, but they were thinking that in the next 5 years you would get to a decent vocabulary with speech recognition, and therefore, well, even these would be a practical thing that could be possible. So that's this paper. That's the paper that outlines this interaction, this relationship between man and machine, and brings them into close proximity. And it is from that you could see that ARPA was already thinking about, of course, there was military applications involved here. The SAGE, sort of the next level of the SAGE system was being proposed, being able to make fast decisions. I think that probably this was enough to sell his ideas to anyone within that military branch, making decisions fast before the enemy strikes and things like that. So he fit in there, but he used his position there to advance other parts. After he gets into ARPA, he brought together a group of scientists, and he kind of jokingly called the group the members, the Intergalactic Computer Network Group. It was a joke. He did not think that this was something that was, and it hasn't really stuck anyway. But he said, okay, that's kind of puts it into this long-term perspective, I suppose. But also because, and you will see in a minute, the intergalactic part refers to the fact that you have different species talking to each other, namely the different kinds of machines. And in this memo that he sent to this group shortly after he took his post at ARPA, he writes what he's looking for. And I've highlighted here one part. Is it not desirable or even necessary for all the centers that are linked together on this network to agree upon some language, or at least upon some conventions for asking such questions as, what language do you speak? And then he continues to talk. He basically starts talking about we need some kind of a neutral language that we can all speak that allows us to route traffic, essentially, data between different kinds of machines, and to find out what resources are available on the other side, to inspect a computer to see what are your programs and can I use any of them to deal with my data. So this is what he's doing in 63. In 68, this paper comes out, the computer as a communication device. And this is, here he kind of summarizes also some years of thinking about this. And this kind of looks a little bit into the future of this that has now already started taking place. So in 68, like I said, showed in the timeline, that's when the call for proposals for the internet really came out. And this is kind of cool, almost like accompanying that and saying, here is what the internet will really allow us to do. Well, he started his paper saying that in a few years, men will be able to communicate more effectively through machines than face-to-face. Probably trying to shake up a few people there. And he has, as an example, he said in 2 days, there was a group that accomplished more with the aid of computers than what would have taken 2 weeks. And I'll come back to this example in a minute. But he was in the strong belief that involving computers in human-human communication, that communication would improve. We have to think a little bit about, okay, what does he talk about? What does he mean by communication? And he says, do two tape recorders communicate when they play to each other and record from each other? I think we all agree that two tape recorders would not be considered to be communicating with each other if they just play, record. We want to emphasize something beyond this. It's one-way transfer. The increasing significance of the jointly constructive, the mutually reinforcing aspect of communication. When minds interact, new ideas emerge. We want to talk about the creative aspect of communication. So he's just clearly saying that communication is something more, and we should be concerned about that creative aspect, this joint work that goes on. And to understand this a little bit better, he talks about what a model is. And a model is a conceptual structure. It's an abstraction that initially is only in the mind of one person. So I do something thinking, it's an abstract thing, and it's a model in my head. And society rightly distrusts the modeling done by a single mind. So me walking around with this model is not of any help to society, and you would not trust me if I said, I have this model. Therefore, we require communication. We require cooperative modeling to be accepted. And during face-to-face communication, that's when these models get externalized. We place them out there for others to see, for having this kind of joint communication happen. And that perhaps two-way telecommunication, here they're saying like telephone calls, for example. When we try to talk on the phone, we're not always successful in doing very effective things when we want to do some abstract thinking. So perhaps two-way telecommunication falls short of face-to-face because it fails to provide the facilities for externalizing models. So that's kind of a nice way to criticize certain communication media. Do they support or not support the externalization of models? And I'm gonna open the window a little bit here. Now there's this new medium, the digital computer. And he is basically saying that this new medium is finally allowing us to externalize these models in an effective way when we communicate with each other. Think of this new medium as an amazing kind of placeholder of our model that we can then dynamically manipulate with other people and therefore update our model. And then once we have all had a chance to work with it, it is no longer the thing of a single mind, it's a thing out of several minds, and we bring that with us back. And he really emphasizes that this medium is programmable. So it has capabilities to represent process, not just data. So we can represent models that involve processes, and we can criticize them, we can observe them, and we can use them as resource to our thinking and communication. And this is a big difference from other media, such as books, where someone publishes a model and says, now read about it. Here, you can invite others to participate in your modeling through programming. And there were experiments done exactly along these lines, which was not his projects, but he was involved in. So at Stanford Research Institute, Doug Engelbart was constructing a lab that was looking into this interaction between man and machine, and they set up a project meeting room where every person would have a display in front of them. So you sat around the table and you'll be looking at the display, and then everyone would have keyboards and mice. And this is in, oh, I didn't put the date, sorry, this is 1968, and this was the first real use of mice and hypertext and so on. There are tons of interesting things happening there. But this meeting allowed someone to display the results of running a program on a screen that everyone would see. And they would basically progress through the meeting by observing different things on, and manipulating different things. And this was kind of a proof of concept. This is the meeting that he referred to in the beginning when he said that it took only 2 days to conclude this meeting that otherwise would have taken 2 weeks. So the technology was helping people in the same place reach a conclusion faster. And again, the programs that you could run on these machines were important. Well, it is not always good to bring the individuals or the individual problem solvers always into a meeting. And I think it's kind of funny that so why is that case not always a good idea? Because many of these problem solvers see themselves as kings. You bring them into one place, one institution, there's not enough seats for kings in there. Someone will have to feel bad or something like that. So let them just stay at their different locations. But we still need their ideas to get into contact with another. So we still need what they're doing to interact and others to interact what they have. And therefore, we need to build an interactive community of multi-access computers where all these problems and programs are being stored and being worked on. And at this time of this writing, there already existed a few what he calls socio-technical pioneers, and that are kind of almost leaving the rest of the computer world behind because they are communicating so fast, and they're allowing, they're coming sharing their programs and models of things. And what he wanted to see was the connection of all these smaller communities. There was only six communities that had this ability to log on to each other's computers. But he wanted to create a super community. All universities in the same community. We need to make the response time short and conversation free and easy, so that people will actually participate in this communication. He describes message processing as the backbone for this, and this is basically packets, the idea of packet networks, where you have a message processor that can move things around the network. You split the idea of control and data. So any packet has a control portion that allows it to flow into the right place in the end. And then you have a payload in terms of the data. And if you focus on the control and you make that robust and make that accessible to everyone, data can flow anywhere in the network and information can pass. And anyone in this network would be able to access a program anywhere else on the network, even if they're run on different platforms. Fine. And that is actually a super important idea. So now if you go back to his psychoacoustic days, sitting at BPN, he would now be able to run algorithms on specialized machines, maybe supercomputers with special abilities, to give him answers quickly. And at this time of writing, that's when they had that first experiment already being successful, although at this point they had not formulated the protocols of the internet. And this is the last slide, and this is really forward-looking. He saw the future as being very happy, if we do the things right, What will the online community be like? Well, these are communities of common interests and not location. So we will be gathered with the people that we like to spend time with because they are like-minded or something like that. So we don't have to worry about accidentally ending up next to someone and then having the forced conversations, I suppose. So he was really thinking about life being happier because of that, and also that, of course, more effective and productive in conversation when we can have access to all of this data and all these modeling tools to make communicating effective. But also, he was very interested in this idea of plenty of opportunity for everyone. So if you're stranded in one physical location in the world, someone will still want and need your intellect or your interest. And you only have to become part of the network to really be to be able to do what you like to do best and be part of something bigger. And for the society, the impact will be good or bad, depending on this last question. Will to be online be a privilege or a right for only a few? And that's kind of, this sets, I mean, this is the tone of the internet. The original idea was it needs to be for everyone. Otherwise, we have failed. And this is also what we are still today trying to protect. If we want to make the society a happy place, this needs to be a right for everyone. So that was the end of this presentation. There's a few references. I may have missed a couple, but there's plenty out there. But thank you. Any questions in 5 minutes? Or discussions? I mean, yes, right.
So how would you say that he influenced you for your work?
This is kind of interesting. I mean, I am sort of in the same position as you. I mean, I did not know him until I started delving into the history of the internet, because that to me is a really fascinating concept. And just reading, these materials, I realized, well, okay, these ideas go back quite a bit. So I would say I was not directly influenced, but the fact, okay, I mean, you just kind of feel that spirit everywhere around you when you actually are interacting with some of the pioneers of the internet. I mean, those that actually worked with them, and they are still working on the internet, and you can see that I think the legacy continues. I could say maybe coming back to it, it helps you, it kind of re-inspires you. Like, okay, if you've been doing the same thing for a little while, and then sometimes it's kind of fun to read some of these old idea papers and kind of pop off the stack a little bit, see what's really underneath, and kind of here are some of the fundamentals that maybe we should make sure we don't lose sight of. So I think maybe in that sense, he's influencing just my current way of thinking, because the fact that we're getting back in touch with these original ideas helps us to maybe take some bigger steps forward. All right. Thanks a lot. Yo. Okay. Yeah, I reused that image from. So that's the American TV. The American military established a base in Iceland after the Second World War. And around that time, they started broadcasting TV signals. There was no state TV. There was just the American TV coming from the base. And the Icelandic public protested, or some of them, saying that this was, basically American cultural invasion.
So it kind of marks some monumental moment in the history.
It's a monumental moment both in terms of technology, because you had these broadcasts, and in terms of society. Because people ran out and bought television sets to receive the American television. Yeah, and then the only thing you got was from them. Yeah, exactly. Thanks. All right, yeah, rétt náði þessu inn í klukkutíman. Ég held ég hafi stoppað það. Ég held ég var að stoppa það, sko. Oh, stop broadcasting.